Welcome to this video on multiplying fractions. We have already introduced the concept and the idea of multiplying fractions and done several examples. Now what we want to do is we want to clarify some common misconceptions regarding multiplying fractions. So as we go through these questions, I want you to take a minute, pause the video, formulate your own answer, and then unpause the video to see if you're correct. So the first question is this: true or false? A common denominator is needed to multiply two fractions together. So really simple example, let's say I had 1/2 times 1/3. Do I need to make 1/2 and 1/3 have the same denominator before I multiply them? Okay, well the answer is false. In fact, if I did that, I would not get the correct answer. So when you need common denominators, because that's probably a thing that may be floating around your head somewhere, right? Well, it's not to multiply two fractions together. When do we need that? We actually need common denominators when we add or subtract fractions, okay? So common denominator, if you remember that concept, okay, comes in when we add or subtract fractions. Okay, so the reason this is important is many times students learn the multiplying and dividing fractions right around the same time that you're also learning to add and subtract fractions, or relearning it, right? So what can happen when you learn a lot of material all at the same time, right? It all kind of gets cluttered and mixed up. Like, have you ever gone to a party and you meet like 5 new people and you're like, later on you're talking to one of those 5 people and you're like, gee golly, are you the person who's has a pool in their backyard, or are you the person who just took a ski trip to Colorado? Like, you, right, you have all this information and it's just kind of all mixed up in your brain, right? And you don't remember who is who. Okay, so that's kind of what can happen when you learn a lot of information all at the same time. It gets mixed up. Okay, so when we talk about common denominator, we're talking about adding and subtracting fractions. Remember, with multiplying, right? So let's put this back and make it back into a multiplication problem. So to multiply 1/2 times 1/3, right? It's really simple. All we do, remember, is multiply across. 1 times 1 is 1. 2 times 2 times 3 is 6. Okay, so the final answer is false. Okay, so that's a common misconception, especially after you go through and you learn how to add and subtract fractions. Then you get confused with the process of multiplying fractions. All right, second misconception I want to address. You can reduce and then multiply, or you can multiply and then reduce. So we'll do a really simple example here. Let's say I have 2/7 times 1/4 here, right? So one thing I could do is I could multiply across, right? 2 times 1 is 2, 7 times 4 is 28, right? Then I look at that and I'm like, wait a minute, right? I don't know why I wrote it that way. 2 goes into both of these numbers, right? So 2 divided by 2 is 1, 28 divided by 2 is 14. Okay, so this is an example of multiplying first. So we know that we can multiply first and then reduce, because we just did that, right? But what if I wanted to reduce first? Can we do that? Well, absolutely. 2 goes into 2 once, 2 goes into 4 twice. Okay, so now I have 1 times 1 is 1, 7 times 2 is 14. Okay, so in that second method, I decided that I was going to reduce first and then multiply. So this question is absolutely true. So you can multiply across and then reduce. You can also reduce first and then multiply. All right, next question. Multiplying across is the same as cross multiplying. And you can probably guess from this cute little table that I have that the answer is, in fact, false. So let's start over here. I know it's kind of backwards, but let's start with the multiply across. We multiply across when we have or it says an, and what we mean here is an expression. Okay, and I'll explain that in a minute. So the example here is -5/7 times 3/10, right? So remember, we just finished saying when we have fractions that we're multiplying, we simply multiply across. So you get -15/70. Of course, I could have reduced first, but as you can see, I didn't. So I'm going to reduce at the end. So -15/5 is, -15 divided by 5 is -3. 70 divided by 5 is 14. Okay, so I multiply across when I have an expression. Well, what do I mean by an expression? Well, I literally just mean, something like -5/7 times 3/10. Okay, it's different from an equation because, as the word equation, it sounds like equate, doesn't it? Right, meaning I have an equal sign. Okay, notice that if I look back over here, right, in this problem, there is no equal sign anywhere to be seen, right? It's just a multiplication, okay? So it's an expression if it doesn't contain an equal sign. If it does contain an equal sign like this guy, then it is an equation, okay? So if you do not see an equal sign, you cannot cross multiply, okay? So in this problem, we have negative 5/7 equals 3/10. Obviously, that is not true, but, if it were, I would be able to multiply across and, usually what you would have is you wouldn't have negative 5/7 equals 3/10. You would have negative 5/7 equals, for example, x over 10, right? And then you would multiply across, and you would get negative 5 times 10 is equal to 7x, and then you would have to solve, okay? Again, the only point of this whole thing is just to say that that is not true, right? We are not talking about cross multiplying, and it just gets confusing because of the English language, right? Multiplying across, cross multiplying is kind of basically the same word, just flip-flopped. Okay, so please, 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 please be careful when you're multiplying fractions. Remember, we're multiplying across. We multiply the numerators by each other. We multiply the denominators by each other. Okay, the takeaway here is we are not cross-multiplying. In other words, we're not doing this, right? We're not doing 7 times 3 and negative 5 times 10. So be careful with that. Okay, so now I have just a bunch of examples that I want to go through. Again, the best approach to this video, if you want to get the most out of it, is to pause the video, try to do the problem yourself, and then unpause it to see if you were correct. Okay, so for number 1, we have 5/6 times 7 over 9. So you could try to reduce. However, I don't believe there is anything that you can reduce in this particular problem. So we're going to do 5 times 7, and that is 35. We're going to do 6 times 9, and that is 54. So that is our final answer. Okay. Again, if you're like, gee, I don't know, I'm not sure if they have anything in common, right? You can go back to 5 and 6. 5 and 6 can't be reduced. What about 5 and 9? Nope, nothing there. Right? What about 7 and 9, right? 7 9s can't be reduced. What about 7 and 6? Nothing that can be reduced there, right? So if the building blocks, right, there's nothing that goes into any of those numbers, if they can't be reduced, then the final answer also cannot be reduced. Okay? If you're still just really worried and stressed out and paranoid, just one more trick that I'll give you, one more trick you can have up your sleeve, is you can always create what's called a prime factorization tree. Okay, so 35 is 5 times 7. 5 and 7 are both prime numbers, and I have a whole video on prime factorization if you want to watch it. Okay, so 5 and 7 are the smallest we can go. If I look at 54, it's 6 times 9. 6 is 2 times 3. 9 is 3 times 3. Okay, so if I write out the prime factorization of each number, right, so the prime factorization of 35 is 5 times 7, the prime factorization of 54 is 2 times 3 times 3. So I could literally write it like this, 5 times 7 divided by 2 times 3 times 3 times 3. Okay, and you can always do this. This is a valid method. And as you can see here, right, as I look at the numbers in the numerator and the denominator, nothing matches up. Right, there's nothing in the numerator and the denominator that can cancel out. Okay, so again, that is just one more tool that you have, one more method that you can use if you're just really worried or stressed out or insecure about, not knowing if a fraction can or cannot be reduced, because many students have that question. Okay, so let's go to number 2. So number 2 is a little bit different, looks a little bit different. First of all, we have parentheses. So remember, parentheses are just another way of indicating multiplication. They're kind of the tuxedo of multiplication. So all we really mean here is we mean that we have 2/3 times negative 2/3. Okay, so if the tuxedo with the parentheses make you uncomfortable, you can always rewrite it this way. Okay, so again, we're just going to simply multiply across. 2 times negative 2 is negative 4, and 3 times 3 is 9. Okay, and that is as reduced as it gets. But again, let's say you're like a little bit worried or insecure, not sure, right? Well, 4 is 2 times 2, and 9 is 3 times 3. We'll just keep that negative sign hanging out there. Okay, so 2 times 2 is the prime factorization of 4. 3 times 3 is the prime factorization of 9. So you can see by writing it that way that there isn't any way to reduce 4 over 9 or negative 4 over 9. Okay, so that's number 2. Number 3. Okay, this time we have 2 negative signs, right? It's true that one's in the top, one's on the bottom. Well, what do we get when we multiply a negative by a negative? Well, a negative times a negative, you might recall, is a positive number. If you're not sure, you could proceed by just multiplying across. Remember, multiplying across is very different from cross multiplying, so watch that. Okay, so we get negative 12 over negative 77. Okay, a negative divided by a negative is a positive. Okay, again, let's say I have a moment of fear and insecurity, wondering, gee golly, is there any way that I could possibly reduce this, right? And one strategy you have, you don't have to use it, right? But it's a lifeline, it's there if you want it, is you can rewrite this as a prime factorization. So 12 is 2 times 2 times 3. 77 is 11 times 7. If you're like, gee golly, Heather, how do you know that? Well, I've been doing this a long time. Okay, if you don't know that, right, you could just draw your little tree. So you could maybe think to yourself, well, 12 is 6 times 2, right, and then 6 is 2 times 3, right? As soon as you get to a number that's prime, meaning it can't be divided by anything besides itself and 1, right, then you have to stop. So it would be 2 times 3 times 2. Right, with 77, obviously 7 goes into it, so it's 7 times 11. Both of those are prime numbers. So 77 is 7 times 11. Okay, so again, this prime factorization, you don't have to do it. I'm not looking for it grade-wise, right? It's just a tool that you have if you need it to just comfort yourself knowing that the fraction can't be reduced anymore. All right, this one's pretty different looking. So we have in parentheses negative 7/9 times negative 5. So the big scary thing here, right, is that negative 5 isn't a fraction. Right, the other thing that might be alarming is that you have parentheses, which we don't really need, right? They're not really doing anything for us. So I could just rewrite the negative 7 over 9 without the parentheses. And then the other thing I want to do, because it really, really helps me, is I'm going to rewrite negative 5 as negative 5 over 1. And you can always do that, right? If I'm like, hey, I ate 3 pizzas, right? That's like 3 pizzas divided by 1 person, meaning I didn't share them with anyone, right? So if you divide by 1 or multiply by 1, your value does not change. Okay, so we're going to multiply across. So we have negative 7 times negative 5. That's going to give us a positive 35. And then, of course, 9 times 1 is 9. Okay, there is nothing that can be reduced. But again, let's say you're just kind of panicking or worried or something. The prime factorization of 35 is 7 times 5. The prime factorization of 9 is 3 times 3. So if I write these two numbers out as their prime factors, a product of their prime factors, I can see that nothing cancels out. All right, number 5. We have 6/7 times negative 2/3. Okay, so remember, I don't really need that tuxedo, right? I don't really need those parentheses. They're probably just there to emphasize the fact that the fraction is negative and to group them together. So this is the first fraction, this is the first problem we've had where we could, if we wanted to, we could reduce first before we multiply. So do you see how we have a 6 divided by 3? Well, 3 goes into 6 2 times, 3 goes into 3 1 time. So now that I've reduced, right, basically what I've done is I'm like, oh, I have 6/3. I can reduce 6/3 to 2 over 1, right? That was the previous section that we've already done. So having done that, right, now I have 2/7 times negative 2 over 1, right? So now I can just multiply across. So 2 times negative 2 is negative 4, and 7 times 1 is 7. So my final answer is negative 4/7. Let's see if I could have gotten the same answer by multiplying and then reducing. So 6 times negative 2 is negative 12. 7 times 3 is 21. So I can see that negative 12 over 21 is not the same as negative 4/7. And that's simply because once I get to negative 12 over 21, what I need to do is I need to reduce. Okay, both of these values are divisible by 3. So negative 12 divided by 3 is negative 4. 21 divided by 3 is 7. Okay, so if I multiply first, that's fine. I just have to make sure I reduce. And when I do, then I get the same answer as reducing first. All right, next one. So again, we have this situation here where we have a whole number, right? We have, or not a whole number, but an integer. We have negative 3. Okay, because it's not a fraction, I'm going to do one extra little step, and I'm going to make him into a fraction by putting him over 1. Okay, so once again, this is an example where I could reduce first. So 3 divided by 3 is 1. 15 divided by 3 is 5. So now I have negative 1 times 4/5 So my final answer is negative 4 over 5. Okay, what would happen if I decided that I wanted to multiply first and then reduce? What would that look like? Well, I have negative 3 times 4, that's negative 12, and then I have 1 times 15, which is 15. So as you can see, negative 12 over 15 is not the same as negative 4 over 5. So of course, what I just have to do is I have to realize that both of these numbers are then divisible by 3. Dividing both things by 3, I get negative 4/5. So again, if I remember to reduce at the end, I do end up with the same value that I started with. All right, number 7. So notice I have two negative numbers. Remember, a negative number times a negative number is a positive number. Therefore, my final answer must be positive. Keep that in mind. Okay? Another thing to think about is that we can reduce and then multiply. 3 divided by 3 is 1. 15 divided by 3 is 5. Okay? I can also reduce the 4 and the 8. 8 divided by 4 is 2. 4 divided by 4 is 1. So now I take the leftover numbers, right? I have negative 1 times negative 2. Negative 1 times negative 2 is positive 2. Then on the bottom, I have 1 times 5. So my final answer is 2 over 5. Again, notice it's positive because I just multiplied two negative numbers together. What if, instead of doing it that way, I decided to multiply first and then reduce? Would I get the same answer? Well, let's see. Negative 3 times negative 8 is positive 24. 4 times 15 is positive 60. So, as you can see, 24 over 60 is not the same as 2/5. So, of course, what we have to do is we have to reduce. So, 12 actually goes into both of these numbers. 24 divided by 12 is 2. 60 divided by 12 is 5. All right, let's do a few more examples. Number 8 is 3/4 times negative 16 over 9. So again, we have the opportunity, if we want to take it, to reduce first. 3 divided by 3 is 1. 9 divided by 3 is 3. Okay? We can also reduce. 4 divided by 4 is 1. 16 divided by 4 is 4. Notice that I'm ignoring the negative signs when I reduce. I'm just leaving the negative sign there. So now I have 1 times negative 4. That's negative 4. And I have 1 times 3, which is 3. So this problem gives me negative 4/3. But what if I decided to multiply first and then reduce? Well, we would get 3 times negative 16. That gives me negative 48. Then we have 4 times 9, which is 36. So you can see right now that these two fractions are not equivalent. What I would have to do is I would have to divide by the GCF, which in this case happens to be 12. So negative 48 divided by 12 is negative 4. 36 divided by 12 is positive 3. So again, you can multiply first, but then you must reduce. So if you do your work correctly, then both methods, again, they're valid as long as you remember to reduce at the end if you decide to multiply first, and you should get the same answer. All right. Number 9, we have 4 over 65 times 13 over 100. So again, if I want to, I can reduce first. 4 divided by 4 is 1. 100 divided by 4 is 25. What about 13 and 65? Do they go into each other? Well, if you want, you can type into your calculator 65 divided by 13, and you will get 5. So 13 divided by 13 is 1. 65 divided by 13 is 5. So now we multiply across. 1 times 1 is 1. 5 times 5 is 125. So my final answer is 1 divided by 125. So what if I had tried to multiply first and then reduce? Well, I'd have 4 times 13, which is 52, and then I'd have 65 times 100, which is 6,500. Wow. Okay, so then I have to figure out, well, what is my GCF? And it turns out, in this case, my GCF is 52. And if I divide both numerator and denominator by 52, I do get the same answer. So I want you to notice with these sorts of problems, right, the bigger and bigger my values get in my numerator and denominator, right, the harder it's going to be to get from here to here. Okay, so I strongly encourage you and recommend that you take some time and try to reduce first. Okay, if the reducing thing is hard for you, if it's confusing, you can, I don't know if this will help or not, but you could actually rewrite it like this. This is the same as 4 over 100 times 13 over 65. Okay, if that helps you visualize it better. And then, right, I could reduce this fraction. 4 over 100 reduces to 1 over 25. I can also reduce this fraction. 13 over 65, we said, was the same as 1/5. And then I multiply those across, and I get 1 over 125. Okay, so there's a lot of different ways to look at it and see it. So find the way that is going to be the perfect way for you, that works best for you, and then stick to that way. Don't try to jump back and forth between different methods. Okay, last but not least, we have 5 divided by 0 times 0 over 10. So I really want you to pause this video, think about what the answer is going to be, and then unpause it and see if you're right. Okay, so one method would be to just completely jump in with both feet and just multiply across. Well, anything times 0 is what? Is 0. So 5 times 0 is 0. 0 times 10 is 0. Well, remember, right, we can't divide by 0. And when we try to, we get what? We get an answer that is undefined. Okay, so that's one way to understand this problem. Okay, if you don't like that way, another way to think about it is that 5 divided by 0 is already undefined, isn't it? Right? So I can't multiply, right, 0 over 10 is just 0, but I can't multiply 0 by something that doesn't exist. That doesn't make sense, right? So either way you think about it, if you want to think about it as, that we can't perform this operation to begin with because we're working with a number that's undefined. You can think about it that way. If you want to think about it as multiplying across and getting 0 over 0, which by definition is undefined, then you can think about that way as well. Okay? Please do not be tempted to think that these cancel out, right? So again, 0 divided by 0 is not 0, it's not 1, it is undefined. Again, as soon as you see 0 in the denominator, right, you can just stop what you're doing, write undefined, and move on with your life, okay? Because you can't have 0 in the denominator.